So, what is consensus? In the computer science world, consensus is what happens when different computers try to agree on something. One example of this is the Bitcoin payment system, where a distributed group of participants must agree on the order and validity of electronic transactions. In their 2014 white paper, The Ripple Protocol Consensus Algorithm, David Schwartz, Noah Young, and Arthur Brito provide a deep dive into their own consensus algorithm. The selling point is the ability to reach consensus quickly, something that couldn't be readily said about consensus protocols that came before it. As a disclaimer, this paper does not reflect the current state of the XRP Ledger. This paper is purely kept alive for historical reasons and interests, but it should not be used as a reference. We'll do a reading of the more up-to-date white paper in a later episode. This is the White Paper Center, brought to you by Randall Richard Raymond. So, as of the time of this paper's writing, consensus protocols were being increasingly used to create distributed payment networks such as Bitcoin. In these payment networks, network participants must reach consensus over the state of the network, which is usually the balance of each currency holder. The authors cite three goals when it comes to creating a distributed payment network: correctness, agreement, and utility. Correctness is the idea that network participants can discern between a correct transaction and a fraudulent transaction. For example, a transaction in which someone claimed to be someone else would be considered a fraudulent transaction. Agreement is the idea that there's a single agreed upon history of transactions, even though each node in the network maintains its own copy of the network state. This is different from correctness, where correctness is a property of individual transactions. By contrast, agreement refers to the agreed upon state of the network by all network participants. An example of a network that's not in agreement is if it allows a double spend to happen, or in other words, someone used the same funds twice. Finally, utility is a term used to describe the usefulness of the distributed payment network. The authors argue that a payment network that takes a year to process a single transaction is not necessarily useful. These challenges have a history that goes beyond blockchain and distributed payment systems. They go back to a problem known as the Byzantine generals problem. The Byzantine Empire was a continuation of the Roman Empire that survived into the Middle Ages. In the Byzantine generals problem, Byzantine generals each control a portion of the army. They must coordinate their attacks to defeat their enemy. In order to coordinate, they pass messages between one another using a messenger. However, reaching consensus over the attack can be troublesome. Messengers might not make it to their destination, and some generals may be traitors. Similarly, distributed payment networks are susceptible to the same type of consensus failures. Messages might not reach other nodes, and some nodes may be acting in such a way to harm the network. We call the latter class of failures Byzantine failures. So the authors present a distributed payment system that they call the Ripple Protocol. In the paper, they go over a consensus algorithm that allows the Ripple Protocol to achieve its goals of correctness, agreement, and utility. So let's dive in. So let's define some terms that will be used as we describe the consensus algorithm. A server is just a computer that participates in the consensus process. The ledger is the state of the payment system. It's the balance of each currency holder in this system. The last closed ledger is the most recently agreed upon state. You can think of it like the most recently added block in blockchains such as Bitcoin and Ethereum. Next, people who send money broadcast their transaction to some server, right? And remember, servers are just nodes. Servers will take those transactions and add them to a pool of yet to be approved transactions. This pool of pending transactions is called the open ledger for a server. The unique node list is a group of servers that a server talks to during consensus. A non-faulty server, or a non-faulty node, is a node in the network that behaves honestly. By contrast, a faulty node is a node in the network that commits some sort of consensus failure that can be either honest or Byzantine. And remember, Byzantine failures are failures where the node tries to commit some sort of fraudulent action. Now, for the last three terms, which are probably the most important terms, and these terms are safety, liveness, and fault tolerance. These terms are not just applicable to the Ripple consensus algorithm, but also to any consensus algorithm. So let's go through each one very carefully. First, a consensus protocol guarantees liveness if all nodes reach a decision in finite time. What do we mean by decision? Well, whenever a node sees a transaction, it needs to make a choice. Should it include or discard the transaction? That's the decision every node needs to make. So going back to our understanding of liveness, a consensus protocol guarantees liveness if all nodes reach a decision on whether or not to discard or include a transaction in finite time. A consensus protocol is safe if all nodes reach the same decision of either discarding or keeping a transaction. And this decision needs to be valid. What that means is the transaction was kept only if it was correct and valid given the protocol rules. Finally, fault tolerance is a measure of the number of faulty nodes the consensus algorithm can tolerate. The authors state that it's proven that no answer to the Byzantine generals problem is able to operate with more than 1/3 of its network containing faulty nodes. A consensus algorithm that's able to maintain liveness and safety, given a fault tolerance threshold, should be able to satisfy the original payment system goals of correctness, agreement, and utility. And so we'll see how the authors attempt to show this in their algorithm. Now, one last thing before getting into the consensus algorithm, let's talk about some existing consensus algorithms that came before this consensus algorithm. And the authors mentioned these in a section within the paper. First, they reference a 1985 paper written by Fisher, Lynch, and Patterson, where it was discovered that a consensus protocol cannot achieve liveness if consensus is asynchronous and there's at least one faulty node. Okay, so we remember what liveness is, right? That means eventually the consensus algorithm will reach a decision in finite time, right? So the argument from this paper was that a consensus protocol cannot achieve liveness if consensus is, first of all, asynchronous. Now, asynchronous consensus is consensus that makes no assumptions about when nodes in the network hear messages or how fast they respond to the messages. So a faulty node might never respond to a message, for example, if the computer crashes. So again, asynchronous consensus, we don't make assumptions about how fast nodes will respond to messages, right? So it kind of follows intuitively that if you can't make those assumptions, if there's one faulty node in the network or one that has a computer crash, you never know when consensus is going to end because that node will never be able to contribute to consensus. The authors also cite examples of other consensus algorithms that reach 20%, 25%, and 33% fault tolerance. So when we talk about fault tolerance, we usually discuss it as a percentage, right? What percentage of nodes can we tolerate that are acting in a incorrect manner? For the Ripple Protocol consensus algorithm, the authors claim they can achieve 20% fault tolerance while maintaining safety and liveness. The authors dive into the specifics of their consensus algorithm. First, each node builds a list of valid transactions. Remember, this is called the open ledger. These transactions are exchanged or proposed to other nodes in the node's unique node list until every node in a given UNL, which stands for unique node list, has the same candidate set of transactions. Each node votes on the transactions in the candidate set such that the transactions which do not receive enough votes do not move on to the next consensus round. The final round of consensus, so again, transactions are going through round after round. As the vote threshold moves up, it continues to increase until eventually you reach the final round of consensus that requires an 80% agreement among all the nodes in any given UNL. Okay, so all these transactions that meet this 80% threshold make it into the ledger, and that ledger becomes the last closed ledger. So that gives a brief overview of how the consensus works. Okay, so as a recap, every node in UNL continuously votes on a set of transactions until the final set of transactions has reached an 80% supermajority amongst the UNL. With all this in mind, the authors show how this achieves the consensus properties of safety and liveness while maintaining within the fault tolerance threshold of 20%. Okay. So first, given that transactions need an 80% approval rate to make it into the ledger, it follows that as long as faulty nodes are at most 20% of the network, correct transactions will always be approved, right? So on top of this, the authors argue that the structure of a unique node list can decrease the chances of nodes becoming faulty. If the UNL is large and the nodes of the UNL are chosen in such a way that it would be unimaginable for the nodes to collude together, the chances of faulty nodes appearing becomes very low, right? So this all ties into that safety property. An additional element of consensus safety is whether or not all nodes agree on the same decision. You might realize how this can become problematic since each node has its own unique node list. So node A could be talking to 10 nodes, while node B could be talking to a completely different set of 10 nodes. How do you reach consensus on the same decision if you have completely separate groups of nodes making their own, agreements? The authors argue that for an agreement amongst the network, there needs to be some guarantee of how similar different UNLs are. The authors state that for any two UNLs, more than 20% of the nodes must be in both UNLs. This ensures that all UNLs eventually agree on the same transactions. Okay, so another way to think about this is that there needs to be some mutual nodes that exist between any two given node lists, right? Eventually, this allows for there to be consistency in the decision making amongst all the different groups in the network. Liveness in the consensus algorithm is achieved by detecting how slow nodes are, right? So if we recall back to this whole issue about liveness and asynchronous consensus, we talked about that, kind of extreme example where a node takes an infinite amount of time to respond, right? Imagine you're trying to get, all the votes from everyone in your UNL, but there's just that one node that's just not giving you that vote. It's just too slow to respond. Well, in the Ripple protocol consensus algorithm, if a node takes too long to respond, the node is dropped from the UNL and consensus is tried again without the node in the picture. There are other heuristics that the consensus algorithm uses to make sure consensus terminates quickly. For example, there is a 2-second window for nodes to propose what their transaction candidate sets are for a consensus round. Furthermore, nodes can be flagged for behavior that seems malicious. For example, if a node always votes on, no for a transaction, if a node always says, hey, discard these transactions, it can be thrown out of the UNL. So, as you might already be seeing, by having multiple rounds of consensus, the network can more quickly identify slow and malicious nodes, which will help improve consensus speed in the long term, all working towards the, ultimate goal of achieving liveness in the consensus algorithm. In conclusion, the authors show how their consensus algorithm achieves both safety and liveness given a 20% fault tolerance threshold. Thanks to these properties, the consensus algorithm allows the Ripple protocol to exhibit correctness, agreement, and utility. And that's all we have for you today. In our next episode, we'll be doing a guided reading of Tether, fiat currencies on the Bitcoin blockchain. Thanks for listening, and I'll see you next time.